Hi everybody, I'm glad to be here. My name is Dmitry. Unfortunately, I suffer a bit from jet lag, and so if I will suddenly start to speak about magic ponies, don't be surprised. Yes, I'll talk a bit about myself. I'll introduce myself. I work for JetBrains. I'm PyCharm developer and team leader. And for those of you who haven't heard about PyCharm, it's an intelligent IDE for Python, and it has a strong support of many Python and web technologies. It assists you to develop your application on a very high level with debugging, code completion, and automatic error detection, refactoring, inspections, profiling, and code coverage, many more. And if you have any question about PyCharm, we're here at the conference. You can come to our booth and ask anything you want. I have developed PyCharm for the last 5 years and have created and improved a lot of features there. And one of them, and probably one of the most interesting, is Python Debugger. And today I'm pleased to share with you what I have learned developing Python Debugger. About this talk, I will explain how to trace Python programs. I will describe implementation details of Python Debugger. I will show quite a lot of code. Fortunately, it's mostly Python code. This code actually is the simplified version of the real code that is used in PyCharm and Pydev. Yes, PyCharm and Pydev now do share some code. There's only Debugger. There is a separate project on GitHub that's called Pydev Debugger, and there's the same for PyCharm. So, first of all, why do we need debuggers? As Kernighan wrote in his book, debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. And what we do normally when we need to implement something, we often, but I tend to think that rather almost always, write our code as cleverly as possible. And we get code that we don't fully understand, and as a result, we have bugs that are very hard to catch. The only thing that could save us is a good debugging tool. And we will learn now how to implement one. There are a lot of Python debuggers, but we can roughly divide them in two big groups. The first one is Python debuggers that implemented in Python itself. These are PDB, PyCharm debugger, Pydev debugger. The most advantage of such debuggers is that they are platform independent. They can run on all Python versions like CPython, Jython, IronPython, PyPy. They don't need to be compiled for different operational systems because they are written in pure Python. But unfortunately, this also can lead to a problem. Debugger written in Python share its state with the user program and thus interfere with it, and they can even break each other. For example, if you write sysmodels clear, the debugger will evaporate from the memory and it won't work anymore. But also, that provides great possibilities. Being the same interpreter in the same space, we can do much more. The second group of debuggers are those that are implemented in C. The main debuggers there are WinPDB and one from Wing IDE. They work only for CPython, but they almost don't interfere with user code, and they are, say, more robust in some way. But also they have less capabilities. In PyCharm, we have chosen the first approach, implemented Python debugger in Python to cover all Pythons and to have more features. How to implement Python debugger in Python? All languages provide developers of tools with APIs. Python is not an exception. When we look into Python documentation, searching for debugger API, first we could think that there is none. Then we find some function in a model sys that is called setTrace. What is that? What does it do? If you look into the documentation, we see that it allows you to set a function that will be called every time you get an event from Python interpreter. Event can be call of a function, execution of a line, return from a function, or exception. And the same said for C bindings. So if we want to implement our debugger, and we realize that that is the only entry point, that's the only one function that we can use, we can feel ourselves a bit constrained, if not to say much. But as we know, constraint breeds creativity, and difficult situations breed astonishing results. And in reality, this minimalistic API is quite sufficient. And in addition to Python dynamic nature, it allows you to do whatever you want, and even more than normally is done for debugging in other languages. So how can we use tracing function? Let's see. Here we have a simple tracing function. It is a function with 3 arguments. The first one is frame, that is top of our call stack, that has context and all the variables. The second is event that we get, that is call, line, or exception, or return. And the third is some args that depend on event. Let's just print for every execution line which event we get and the line number. At the line 7, we set this trace function, and we activate it this way. Then we have some simple function foo, where we iterate within the range and print division of some arithmetic expression. And let's see how it could run. After we had set our tracing function on the first line that we will encounter, that will be in line number 13, we have a call or a function that is declared on line number 9. So we get event call on 9. Then we have an event of line on number 10, then line number 11, and we have our output 0.5. Then iteration continues, line number 10, 11, again iteration, another iteration, and we have an exception. So execution terminates. And you see that we have in this short program all 4 Python events that are possible: call, line, exception, and return. And we even know line numbers. And what does it give us? That gives us that we can actually implement debugger with breakpoint handling. Let's do that. Let's make a simple console debugger. To test it, we use a simple program that is the implementation of the ertathens sieve, a function that gets n as a parameter and prints all the primes between 2 and n. And here are our command line debugger. It's actually only 23 lines of Python code. It has 2 main parts. The first part is a tracing function. You know about it already. And here, except only printing of the events, we handle a breakpoint. We have only one breakpoint here. If the current execution line number equals to this breakpoint line number, we just do the simple thing. We read the input from console standard input and interpret it as a command. There are 3 possible commands. The first command is frame. We just print all variables. The second command is C for continue. We resume our execution and proceed to the next stop, if any. And any other string is just treated as an expression. And the second part of this simple debugger, even more simple than the first. We just get the line of the breakpoint and the file that needs to be debugged. Then we set our tracing function and execute the file. So let's look how it works. Here is our simple debugger opened in the editor. And now we just... So we executed it and it stopped on line 6. What we do is we type frame, and we see that our this one, that I is equal to 2 and multiple set is empty. We continue and we type frame again, and we see now that our multiple set is all even numbers and I equal to 3. So we can continue. We can write here something like, so that reminds us PDB actually, but it's only 23 lines of Python code. Amazing. It's very useful. But it's not that useful as it could be. Drawbacks of this console debugger. We can set only one breakpoint. We can set and remove breakpoints during execution. We are unable to present our frame values in a nice view. So what do we actually need is visual debugger. And if we talk about UI and about visual debugging, we think about UI and multitasking, and if we think about that, we need some kind of our architecture, and let's imagine how it can look like. And our architecture can look like something like that. On the left side, you see our visual part, that's IDE, and on the right side, that's a Python process that is being debugged, and they communicate between each other within a circuit connection. That allows us to run them on different machines, enabling remote debugging, for example. And our debugger interface sends breakpoints and comments to the Python process and gets back events, threads, frames, related values, all the data. And in Python process, to handle this communication, we need two threads, one for reading, one for writing. And we use threads here because we don't need actually performance, and global interpreter lock is not a problem for us. But we need cross-platform capabilities. I remind that we need to run it under CPython and Jython and so on. So we use threads. So if you talk about communication, then we need to define a protocol. The protocol for this communication will be quite simple. Every message is just a line separated by end of line character, and all the data inside this line is separated just by tabulation characters. And the structure of the message could be, the first record is common ID, the second is type, common type followed by arguments that depend on common type. Common types can be set breakpoint, resume, get thread, get frame, evaluate expression. And we can send a request, and we expect to receive a response. And we need to measure them somehow, and we use ID for that. A response should have the same ID as a request, and that's it. It's very simple, but yet very powerful protocol. And on the side of the IDE, by that I mean our visual side of the debugger, we assume that it creates a server socket and launches the script for us with the correct command line, and passes socket address and passes a sample program as an argument for the debugger, and waits until the process is connected to the IDE. So let's see briefly how the code could look like. So that's the debugger main code. We just initiate our debugger, and first of all we make a socket connection. We connect to the IDE this way. So yeah, we just connect. The next we initialize our network communication. So for that we just start two threads, reader thread and writer thread. And reader thread can look something like that. It just in a loop reads all the data, and when it finds the end of the line, it reads the whole message and splits by tabs, and then parses the fields, and then puts the comment to the common queue. And the writer is almost the same, so it's very simple. So what next? Next is a bit more interesting. We run our program. To do that, we set our tracing function, and then we wait for a comment from IDE to start, because at this point we need to be sure that all the data from the IDE has just arrived and breakpoints are initialized. When we get a comment from the IDE to start, we execute the file. And the most interesting part is our tracing function. Actually, also very simple. We handle here line events. We take a line number and file name from the frame, and we check whether we have breakpoints for this file and line. And then we just notify our IDE about hitting the breakpoint and suspend the process. Launch and loop just in the tracing function. Let's look at the demo of the visual debugger.
So we have our earth-of-sense sieve function, and now we use the visual debugger. We place here breakpoint, so it's connected, and here we have all the values, and actually that's much better than we had before, but actually it's not much complex. It's all that I've just showed you in Python code plus UI written in Java in the IDE side. So here we can step and resume, and here we have a command line where we can do all this stuff. So yeah, that's it. but that's not it. We miss important features. We just implemented Visual Debugger that communicates with an IDE, but we don't have conditional breakpoints yet, exceptional breakpoints, step over, step into, smart step into. And we should assure that it works on Python 2.4 and 3.4. So, conditional breakpoints. We just, to make them work, we just enhance our tracing function so that we check whether we have any condition associated with breakpoint. And condition is just Python expression that is evaluated to true or false. And if it's false, don't suspend this breakpoint. And that's it. Exceptional breakpoints. To trace exceptional breakpoints, we need to handle exception events. We get our exception type from argument and see if we have an exception breakpoint for this exception. If we do have, we suspend. If we don't suspend. Step into, step over, smart step into, run to line. Step into is just resume and stop on the next line. Step over is also resume, but we stop on the next line to the current position in the same frame. This means that we stop exactly on the next line event in the same frame. And smart step into is just step into, but we stop on the first line event that raises from the frame of the selected function that we selected. And run to line, just a temporary breakpoint that we remove after we reach it. So we have 4 additional features that are just implemented in several lines of code each. Python 2.4 till 3.4. If we have written our debugger in Python, does it mean that it will work for all Python versions? Not exactly. For this to work, we need also to handle all differences in the standard library. So we end up with the code like this. Unfortunately, it's not very much, and we can locate it in some places, but there are many differences between Jython and CPython and between Python 2.4 and 3.4. And we couldn't use 6 for porting because 6 didn't support Python 2.4 till the recent time, but now it supports, so probably we can use 6 now. So, that were prosaic things. Let's dive into some tricks, like multiprocess debugger. That is the point that I like the most, because this feature shows us how our constraint, very limited debugging API, allows us to do something better than in other languages. You can't debug multiple processes in Java, but in Python, due to its dynamic nature and due to the fact that we implement it all by hand, we can do that. For every new process that is created, we just need to run a debugger code inside it automatically. That will connect, this code will connect to our IDE, set the trace function in it, and we get the same like before. And how are new Python processes created in Python? If we go to the Python standard library documentation again, we see that all functions creating new processes in the end use few basic functions. And what can we do with them? Just monkey patch. We do this that way. We take, for example, the function exec from OS module and replace it with our new exec function. And in our exec function, we call the original function with patched arguments. And the patching of arguments is very simple. If it is Python process being executed, we add our debugger script in front of real arguments, the host and the port of the IDE. And then, when it is executed with this Python process, happens the same what happened with our initial process. It is being executed under debugger. And what if we have already a process that is launched, but we also want to debug it? Let's think how we can implement that. The basic idea is to stop somehow all the threads of this running process, acquire the global interpreter log, and execute our debugger initialization code inside this process. This initialization code will set tracing function and connect to the IDE. But how to inject it into the process? Unfortunately, there is no platform-independent way to do that. And also, we need to rely on Python interpreter internals. So it is CPython only now, but still there are platform-specific tools. On Linux and Mac, we have GDB and LLDB, respectively. They allow to inject your code into a running process. And on Windows, we need to hack with Win API. That is doable, but we won't touch it today. Let's see how we can do that on Linux. From our IDE, we just run GDB with a special command line. The most of the arguments here are for batch and silent execution in a headless mode. And there are also some other configurations that are not very important now. The main thing is that we pass a process ID for GDB to connect to the process. GDB connects to it and stops all the thread in the process automatically. After that, we ask GDB to load our dynamic library and call a function, do attach, that is stored there. And do attach simply acquires, it's written in C, it simply acquires global interpreter log with the Python interpreter, then evaluates our debugger initialization script. It evaluates it as a string by a system function of the Python interpreter named pyrun simple string. And our tracing is initialized in the debugger with such code. This is very simple. And that's it, exactly what we wanted. And now I can demonstrate you both of the features I talked. So multiprocess. Here we have a simple script that starts our errata_thens.py. Let's debug it. We place breakpoint here, and we debug it. So we can step over, and let's pay attention. We have attached to it. So here, I've been talking about GDB, but LLDB is quite the same. It differs only in command line arguments. And we can place now breakpoint, and it stopped. And we can, for example, set value to, and what do we have? So yeah, it works. One more trick, debugging of Django templates. First, probably first I show you again how it works, and then I explain how it is implemented. Here we have a simple Django project. It's the canonical sample, like Paul's project. And we have here a Django template file. Let's put breakpoint just here, just in the middle of the template file. So we start our Django server under debug. And it works. We stopped just inside the rendering of the template. And here we can also step through the nodes, and we can see all the data inside the template. And of course we can change it like before. How is it implemented? Actually, it looks like it is very tricky, but it's not. It's also very simple. For Python, we have tracing events like call, line, return, exception. And to provide debugging of Django templates, we need something like that, but for template rendering. And how Django templates are rendered? If we look into the source of the Django, we see that the main class template has method render that in the end just nothing more than a render of the nodes list. Nodes lists are compiled tags inside the templates. And what is node list? Node list is nothing more than iteration through the nodes and rendering all these nodes. So that's the answer on our question, how to make this work. We just need to capture all the invocations of method render of the instances of the class node. So we make a simple addition to our tracing function. We check if the Python tracing event as call, and if it is Django render call, then we try to get a template file name from it, and we check if we have breakpoints that are set in template file, and if the template, current template line matches the line number of the breakpoint, we create a virtual template frame that provides variables in the template, and we suspend. And our checking of the Django render call looks like that. It's just we take the name of the function from the frame, and we see if it is render, and if the class inherits node, then we treat it at the render of Django template node. So that's it. And the same thing for Jinja2 templates. Almost the same way. There are some differences, but almost the same way. But to make the code prettier, we implemented both additions to the outtracing as a plugins. And I highly recommend for your plugin architecture in your Python applications the library written by Armin Ronacher, author of Flask, that is called Plugin Base. It's very lightweight and provides you a simple way to add plugins to your applications. So that's it. If you want to dive into details, there is the project on GitHub, Pydev Debugger. Actually, PyCharm is also open source. PyCharm exists in two versions. There is one professional edition and community edition is fully open source. But there is it's based on IntelliJ platform, and there is a lot of Java code there, and all UI is there. But here we have we have painful situation here. I am talking about slide that you don't see. Here, I'm talking about this one, but this one is only Python code, and this is a Python debugger implementation that is extracted from PyCharm main code, and that is, as I've said already, that's shared with Pydev Debugger. So if you are interested and if you want to dive into details, you can look for these models that I was talking about in this presentation. So that's it. Thank you very much for listening, and if you have any questions, you can ask now or visit our booth during PyCon. Thank you.
I'm newbie to Python, and this is the first time I see the demo of a Python, and I'm really impressed by the fantastic feature, for example, for debugging in multiprocess and using GDB to attach the running process. And I would like to thank the fantastic work, thanks Python team for the fantastic work. And I also wondering, may we debug with Python remotely, so we could debug embedded system, for example, or do we already have such a feature, or is one of Python team's future plan?
All the features that I have shown, they exist already. So they are usable for production. So I've just tried to explain that there is no magic there. They look like magical, but it's very simple to implement because of the dynamic nature of Python. Python is so amazing that you can do anything you want there. Python doesn't restrict you. And thank you for the warm words about our product.
Hello. Thank you again for the development of the debugger, because we really needed that in Python. I was interested that you implement the whole thing by yourself, right? Not built upon like PyDB, right?
No, I haven't implemented this by myself, but we didn't use PDB. Actually, our work was based on the debugger in Pydev, which was in its own turn based on some other project. And at some point, it was 5 years ago, we forked Pydev version and added a lot of features there. And then it was a very strange process. Then we added features to our fork, and maintainer of Pydev, Fabio, added his fixes in his fork. And it was not very good. And last year we decided to merge our forks. So that was the time when this open source project was created. So we just merged our versions, and now there is only one.
So I'm interested that why did you choose? Why did you not choose PDB? Was there some kind of fundamental design decision, or are there something that you can do better if you have your own implementation?
You know, there is a saying that code goes to the standard library to die there, and PDB is in standard library, and you can do nothing with it because it's just in stone. And Pydev version was very flexible to change, and we forked it, and we could do everything we wanted. So that's why it was possible for us to do all these features, because it was needed to make a lot of experiments and refactorings inside, and that's why PDB wasn't a solution.
Okay, thank you.
So the problem with using sys.setTrace is that a small part of your debugger implementation runs in the same process as the user code. Compared with other virtual machine implementations like the V8 JavaScript VM or the Hotspot Java VM, they typically have a separate protocol just for debuggers or profilers. After going through all this work, do you think such an interface would be desirable?
Actually, it is possible to write debugger support without being in the same space as user code. So as I told, you can write your debugger in C, and you can interoperate with Python interpreter through the CPython internal API. But for us, that wasn't a solution because we wanted to support all the Python versions. And as for enhanced API from Python team, of course it would be better if Python core developers would think more about developers of tools and provide such great tools like in V8 for profiling and debugging, but it's not the case yet. So you need to struggle to develop debugging and profiling for Python, but as I've said, that sometimes leads to even more featureful results.
Yeah, hello. So thanks for the talk, and also thanks for building the debugger. So my question is that you talked about the multiple process debugging, right? So I've been building some Apache Spark script, Python script, and the pattern is quite interesting that they have a master JVM spawning some worker JVM, which will then use the JPython to run my Python code. And I would like to see, could we like debug in this situation? Like, can we connect to the worker JVM machine and then to debug our Python script, something like that?
It depends, and actually I don't think that it would work just out of the box, because your Jython code is executed from Java, and we don't quite manage this point when it is being executed. So if we talk about pure Python code, whether it's executed in JVM or not, we can handle all the new processes. But if these new processes are executed from Apache, for example, it would be a bit difficult. But that's a direction for us to think. Thank you.
Yeah, thank you.
谢谢 Dmitry 的精彩的 talk。